get, I don't know, your internals are maybe on or after 15th. So, and your exam date has also been announced, right? When is it? 24th March.
No, ma'am, the core courses, that is the CC courses, are on 20th and 21st.
20th, yes, yeah. So, uh, yeah, so keeping more or less at least, you know, a week or two of buffer time between the end of our syllabus and that. So today we'll finish off vector integrals and integration theorems. I'll go a little fast, but the elaborate slides are pretty elaborate, and you get the slides as usual. And then in our next class we'll do the curvilinear coordinates, which I think I'll need. Uh, Finishing curvilinear coordinates in one class is a bit difficult. Let's see. First, let's finish today's class. So you can see my screen now.
Yes, ma'am.
Okay, so we'll start straight away from surface integrals. We finished line integrals and we discussed how a line integral is related to the force, which is conservative or not, and gives us a work done which is path dependent or independent. So today we'll do surface integrals and then we'll do volume integrals. So what are surface integrals? So from the um, name itself, you can understand it is related, it would be something related to surfaces. Okay. Now when we were doing the line integral, if you remember, we used to take line integral of the vector dotted with a small line element like a dot dr. Okay, so that dr, which is equal to dx I cap plus dy j cap plus dz k cap, is basically a small line element, and then we integrate over it. Now, in case of a surface integral, you have to do a little bit of, imagining over here. We have to consider a two-sided surface S. Okay, and one of the sides we will call positive, and the other side obviously we'll call negative. So this two-sided surface, it may be a two-dimensional surface or it may be a three-dimensional surface. A two-dimensional surface would be, like a piece of paper, the top of a table, etc. Whereas a three-dimensional surface would be a cube or a sphere. These are the regular surfaces. You can imagine any arbitrarily shaped surface too. So just remember that we are talking of both two-dimensional as well as three-dimensional surfaces, but the surface needs to be two-faced. So this is basically what I'm talking about. Okay, so this is my XYZ coordinate setup, and this S, as you can see, the capital S. Okay, this sort of I don't know what I have drawn myself, uh, like a thatched roof something. This is just an arbitrarily shaped surface. Just for the time being, just look at S. Don't look at anything else. Just look at the surface S, this curved surface. Okay, so this is, suppose, the surface that we are considering. All right. Now let us suppose that n cap is the unit normal, which we will call the outward normal for the positive side and the inward normal for the negative side. Now, as you can see, this surface S, it has two sides, okay, this top side and the bottom side. So arbitrarily, we will call the top side as the positive side and the bottom side as the negative side. And the normal to the top side will be called the outward normal, and the normal to the bottom side will be called the inward normal. Okay, so this is n cap, which is outward for the positive side or the top side. And obviously you can understand that for different positions on S, the direction of n cap will change. So n cap is constant at a given position, but if you take n cap at different positions, its direction is going to change. Okay. Now we take a differential area ds on S. Okay. So this shadowy portion over here, we call it ds, which is a very small area, okay, on S. And you see we are associating a vector with this area. We are giving this area a vector sign where ds vector is actually n cap ds. Now this association of an area with a vector sign you had learned when we had done the cross product. Remember when we were doing cross product, we said that the direction is perpendicular. When you take the cross product of two vectors a and b, we said that the direction is perpendicular to both a and b, and we saw that geometrically a cross b, the magnitude, gives you the area of the parallelogram formed by the vectors a and b, when a and b are the sides, adjacent sides of the parallelogram. So there we had first introduced the concept of an area being a vector, and I remember I had told you, I hope you all remember too, that this concept of an area as a vector will come back when we do surface integral. So here it is. As a whole, if you take the surface S, you cannot associate any vector with it. If you take the entire macroscopic surface S. However, if you take a small, infinitesimally small area ds on the surface S, then you can associate a vector with it. And what is the direction? The direction is given by the normal to ds. And as the position of ds changes on this surface, the direction of the normal on this surface will also change. Then the surface integral of a vector for this surface is denoted as this. Okay? If you are asked to take the surface integral of a vector A for this given surface S, then this is what they mean. Surface integral A dot ds equal to A dot n cap ds. Okay? As you can see that the value of ds or the position of ds is different. I mean it's a variable quantity. So when you integrate over the surface, you integrate like this. And why are there two integral signs? In the line integral we saw there was only one integral sign. We are used to doing integration with only one integral sign. Here there are two integration signs because whenever you are considering an area, it means there is involvement of two variables. In the Cartesian system, even an infinitesimal area like this, okay, would mean dx into dy. Area of a rectangle means length into breadth. So if the length is an infinitesimal quantity dx and the breadth is an infinitesimal quantity dy, then the area is given by dx dy. So you can see there are two variables involved. So when you do surface integral, you have to consider two variables, which is why for surface integrals we write the integration sign twice, and S written over here means surface integral over the surface S. Okay? Now if the surface is a closed surface, for example if it's a closed cube, if it's a sphere, then to denote that the surface is a closed surface, we draw a small circle over the double integration sign. Okay? When you see there is a circle drawn over the double integration sign, it means we are considering this A dot n cap ds. Okay? So surface integral over a closed surface. Now it may be proven, you do not need to do the proof, although the proof is given in the book of Spiegel, so you can look through it if you are interested. You don't need to learn the proof, but you must know the formula that for a projection R of the surface S onto one of the coordinate planes, we may write this. Okay. This is for the xy plane. Now what is R? Now first of all, let us understand what is the projection. How do you find the projection? Basically, in very lame language, a projection means a shadow. So suppose this is your surface here, okay, and you are considering this infinitesimal rectangular surface ds. Now if you put a source of light over here, I hope all of you can see my cursor. So if you put a source of light over here, then a shadow will be formed on the xy plane. Okay, so this small rectangle on the xy plane is basically a projection of this surface ds. All right, so this will not be d, this will be r actually. So now if you put a source of light over here on the right of the surface, then the shadow will be formed on the xz plane. All right, if you put the source of light over here in front of the surface, then the shadow will be formed on the yz plane. So depending on where you are putting your source of light, a shadow will be formed either on the xy plane or the xz plane or the yz plane. Okay, and it can be proven that a formula like this can be written down depending on which plane you are taking the projection on. For example, okay, so yeah, this is R, I've written R. For example, if you take the xy plane, so this is in accordance with the picture that I've drawn here, that you have put a source of light on top of the surface and the shadow is formed on the xy plane. Then this surface integral, this is an open surface, so you don't need to draw this circle on the integral sign. So this surface integral a dot n cap ds is equal to integral over r. So you can switch from integral over s, which was arbitrarily placed, to integral over r, which is confined to the xy plane. And the integration is like this: a dot n cap dx dy divided by n cap dot k cap. Okay, so k cap is the normal to the xy plane, right? So this is the formula for projection on the xy. Can someone tell me, by looking at this formula, what will be the formula for projection on the xz plane? Can someone do that? Unmute yourself, look at the formula, and then tell me what is the formula if you take the projection on the xz plane.
Madam, a dot n cap dx dz by mod n dot j cap.
Yes, very
Hi
good.
ma'am, n dot j.
Yes, and similarly for the yz plane, it will be a dot n cap dy dz
N dot I cap.
n dot I. Right. So these are the formulae that you'll use if you are asked to find a surface integral, depending on which plane will give you a better, calculation, easier calculation. I shouldn't say better, I should say easier calculation. So depending on the problem, you will choose one of the three planes to find the projection and use this formula. See, I have not used R in all the three formulae. The first one is R, which is on the xy plane, but for the yz plane, I have used R prime because that projection will be different from R. For the xz plane, I have used R double prime because that projection will be different from the earlier two. Alright. So depending on the plane on which you are taking the projection, your formula will change. So let's straight away do a problem to understand how to go about surface integrals. But I'll have time for only one problem, and you have to follow this to do other problems from your book. So the problem is like this. This vector is given. Okay. This vector is given f equal to 4xz I cap minus y square j cap plus yz k cap. Find the surface integral of the given vector over the surface of a cube bounded by the surfaces x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equal to 1. Okay. This is what I am talking about. The xyz plane, and we have a cube which is made by the surfaces. X equal to 0 is this surface, x equal to 1 is this front surface, y equal to 0 is this surface here, y equal to 1 is this surface, the right surface, z equal to 0 is this surface, the bottom surface, and z equal to 1 is the top surface. Okay, so you have to find the surface integral. Now what we'll do is, these are the vertices on the respective axis. There are these are 6 vertices. There will be 5 other vertices. Now we call the front surface 1 and the back surface 2. Okay, the front surface here is called the first surface 1, and the back surface here is called the second surface 2. All right. Now this arrow represents the normal to the front surface. So what is the direction of this normal? The direction of this normal is along the x-axis,
I cap, ma'am.
I cap. Okay. So surface 1, for surface 1, n cap is equal to I cap, so that f dot n cap is f dot I cap, which is 4xz. So in this formula here, we have f dot n cap dy dz divided by mod n cap dot I cap. So f dot n cap is 4xz dy dz, and n cap is I cap. So we have I cap dot I cap. So this will give us just, so I cap dot I cap is 1. So 4xz dy dz. Okay, we have to integrate. We can see there are 2 variables, y and z, and we have to integrate using the boundaries. Now, at this surface here, the value of x is fixed at 1. This is the x equal to 1 surface. So on the first surface, the value of x is fixed at 1. So we can, it doesn't change, right? It is same over the entire surface. So we can write 1 instead of x. So it comes out to be 4z dy dz. Okay. So we first integrate with respect to y, since the y variable is not there. So we write 4z dz and y for this dy. So we remove one integration sign and we have just one integral, 4 y goes from 0 to 1 z dz. So this becomes 1 again. So we have integration z equal to 0 to z equal to 1, 4z dz, which will give you z square by 2. So 2z 0 to 1, which is 2. So for the first surface, this value comes out to be 2. Alright. Now it is not easy to just see on the screen and understand the steps. You have to do this after this class is over. Immediately you should sit and do this problem by hand to understand the steps by yourselves. Okay. Okay. Now for the second surface, the back surface, this is the direction of the normal. Alright. Outward normal we'll take, because that side is the positive side, so we have to take the outward normal. So for surface 2, n cap is minus I cap. So f dot n cap is f dot minus I cap equal to minus 4xz. Now straight away we can write this equal to 0. Why? Because the value of f dot n cap is equal to 0. Why? Because at this surface, the second surface, x is equal to 0. So whatever you do not need to go through this integration, because at the onset you can see that f dot n cap is coming out to be 0. Alright, therefore integration over the second surface f dot n cap ds will give you 0. Okay. Next we have the third surface. So this is the third surface. The right surface is the third surface, and this is y equal to 1. So normal is j cap, as you can see. So for surface 3, n cap is j cap. F dot n cap is f dot j cap. So from here you can see it is minus y squared. So the integration is like this. F dot n cap ds becomes f dot n cap dx dz by n cap dot j cap. F dot n cap is minus y squared, dx dz, n cap is j cap. So this denominator comes out to be 1. So we have integration, double integration, minus y squared dx dz. Now at this surface the value of y is 1, constant at 1. So you put 1 over here. So minus integration dx dz. Now x goes from 0 to 1. So the integration of x will give you 1. Z goes from 0 to 1. So the integration over z will give you 1. So the final result of surface 3 is minus 1. Okay. Next, surface 4. This is surface 4, the left surface. And its normal is minus j cap, as you can see. So surface 4, n cap is minus j cap. So f dot n cap is f dot minus j cap equal to minus y, just y square. Value of y on the surface 4 is 0 entirely. So f dot n cap is 0, and therefore the integration on surface 4 is equal to 0. Alright. So next we are left with surface 5 and surface 6. Surface 5, this is the normal along k cap, and surface 6, this is the normal along minus k cap. I'll go to the next slide. So I have drawn the two normals beforehand. So for surface 5, n cap is k cap. Therefore f dot n cap is f dot k cap, which gives you yz from the expression of f. And at this surface z is equal to 1, so f dot n cap is y. Surface integral f dot n cap dx dy by n cap dot k cap, so f dot n cap is y. This numerator is 1, so integration y dx dy. So you will get y squared by 2021 dx. So half dx. So x by 2021. So result is half. Okay. So for the fifth surface, the value of the integration is half. And finally, for surface 6, I hope by intuition you can understand what the value will be by now. N cap is minus k cap. So f dot n cap is f dot minus k cap, which is equal to 0. So surface integration is 0. So now what is our job? Our job is to add up all these integrals. So the total integral is the sum of all the values that we got for the 6 surfaces, 2 plus 0 plus minus 1 plus 0 plus half plus 0, and the result is 3 by 2 units. Okay. So this is how, when you are given a surface integral, you have to sort of, if it's a cube like this, you'll have to divide it up into the 6 planes. If it's a hemisphere, then you have to take the spherical side and the plane circle, and you have to perform the integration. So what we'll do is, I'll do another problem. Okay, very quickly I'll go through another problem. This is a bit different from the previous problems, which is why I took this. And after going through these two problems, I hope you'll be able to work out most of the problems that are given in test papers. So this is the vector f, 18z I cap minus 12j cap plus 3y k cap. Evaluate f dot n cap ds, where, see carefully, S is that part of the plane 2x plus 3y plus 6z equal to 12 which is located in the first octant. So the key to do surface integral sums correctly is the diagram. It's almost like geometry. You have to be very careful with the diagram. So I've set up the xyz axis, and this is the plane 2x plus 3y plus 6z equal to 12, which is located in the first octant. Okay, so this is the figure that they have asked you to do. All right, so this is the surface, and you have to find the surface integral over this. All right, so f dot n cap ds will be f dot n cap dx dy by n cap dot k cap. Now you have to find the normal to this plane, and I hope you have not forgotten that the normal to any surface is found by taking the gradient. So perpendicular to the given plane is the gradient, and that is 2i cap plus 3j cap plus 6k cap. So unit normal is given by, you have to take the unit vector along this vector, which comes out to be 2 by 7 I cap plus 3 by 7 j cap plus 6 by 7 k cap. All right. So n cap dot k cap, this value over here, as you can see, comes out to be 6 by 7. All right. Therefore, dx dy by n cap dot k cap is 7 by, this divided by 6 by 7, so 7 by 6 dx. And f dot n cap, you can calculate using this, is 36 by 7 z minus 36 by 7 plus 18 by 7 y. So now you are at a position to calculate the integral. Just remember that from this formula of the plane, we write z in terms of x and y. Why? Because my integration will be in terms of x and y, but f dot n cap contains z, so I replace z in terms of x and y because the integration is over the xy plane. So f dot n cap, putting the value of z from here, comes out to be 36 minus 12x by 7. Once again I am telling you, it is not possible for you to follow this very properly through these slides. I have not skipped any steps. So after I finish this, please sit with a pen and paper. I don't know if some of you are sitting with a pen and paper. It would have been very good. Then you could have done the problems along with me as the slides are going. But if you are not sitting with a pen and paper, you have to do this by your hand after this is over. So the integration, we have the value of f dot n cap, we have the value of dx dy by n cap dot k cap. So it comes out to be integration 36 minus 12x by 7 into 7 by 6 dx dy. So you simplify this and you get 6 minus 2x dx dy. Now what we'll do is we'll first integrate y from 0 to y equal to 12 minus 2x by 3. Okay, so for this I'll go back to the figure once. So see, we've taken care of the z variable. Now as x goes from 0 to this point, okay, which will be 12 by 2, y will go from 12 minus 2x divided by 3. As x goes from 0 to 6, y will, reach like this. Y will increase in this manner. So you have to choose. If you had chosen the y variable first, then as y would go from 0 to 4, x would have gone from x equal to 0 to 12 minus 3y by 2. Okay, so we first integrate over y, which goes from 0 to 12 minus 2x by 3. So we have 6y here minus 2xy. So in place of y you put its limits, and this is the final expression that you get, and then it's easy, you just integrate for x from 0 to 6 and the result will be 24 units. Okay, so these are the steps that you need to follow in order to do a surface integral. All right, I will not go very deep into volume integrals because you just need to know that for a closed surface, I mean, for volume integral, you have to understand that a closed surface is necessary. So for a closed surface in space which encloses a volume V, the volume integral is given by this sign, three integration signs a dv, or three integration signs phi dv for a vector field or a scalar field respectively. So you can perform the volume integration for a vector field or for a scalar field. Three integral signs because dv, the infinitesimal volume, if you take a cube, then it is length into breadth into height. So dx, dy, dz in the Cartesian system. So there will always be three variables. So therefore there are three integral signs. So if you have followed surface integrals, then in volume integrals, since the volume is not a vector, it's a scalar at any time, uh, we don't need a formula like this. We don't need a formula like this. So you just have to take the integral and the surface that is given to you, the geometrical surface, and you have to separate the variables, integrate for one variable in terms of the other, integrate for the second variable in terms of the other, and finally integrate for the third variable. So you have to go through a few example problems and do a few by yourself to understand. I'm not spending time on volume integral over here because rather than giving you direct problems on surface integrals or volume integrals, what you get in your exam are applications of surface and volume integrals. Line integral is a different case because the concept of conservative forces is related to line integrals. Okay, but for volume and surface integrals, you rather get applications. All right, so we will straight away move to the vector integration theorems, which are very important as a basic tool which you learn in your vector analysis class in the first sem and then use in several other fields of areas of physics, electrostatics, magnetostatics, quantum mechanics, several other places as you move to your higher semesters. So you need to, just as I told you in case of gradient divergence and curl, which you need to know very well. I mean, by your second semester, you should be able to do gradient divergence and curl like you do division and multiplication. You should be that fluent. Similarly, the vector integration theorems are another very important tool that you need to follow very closely. So the first one is called Gauss's divergence theorem. Now the formal statement is like this: if V is the volume bounded by a closed surface S and A is a vector function of position with continuous derivatives, then the mathematical statement of Gauss's divergence theorem is this: volume integral of divergence A dV is equal to surface integral of A dot n cap ds. Okay. If you look closely, please notice that the surface integral is a closed surface integral. Okay. So this is applicable only to a volume which is enclosed by a closed surface. You cannot apply Gauss's divergence theorem to an open surface. It is applicable only to a closed surface, and as you can see, it is a tool to convert a surface integral into a volume integral. Of course, n is the positive or outward drawn normal to the surface S. Now let us go through the interpretation of this theorem before we go to the doing. I'll show you one problem of the type that comes from divergence theorem. So what is the interpretation? Now, if you remember when we were discussing about flux or the divergence operator, we had discussed what happens when a fluid is moving through a region, and we saw that the mass of fluid passing any area A per unit time is given by A v dot n cap, where v is the velocity vector. Okay. Now suppose you consider a closed volume enclosed by the surface S. This is an arbitrarily shaped surface S, but this is a surface that encloses a volume. So it's a closed surface. Okay. And we denote ds to be an infinitesimal area on this surface with the normal n cap. So ds is again an infinitesimal area, and on this we have the normal n cap. Okay. So the mass of fluid, according to this formula, the mass of fluid passing through the surface ds, this surface, will be area multiplied by v dot n cap. So ds into v dot n cap, or v dot n cap ds. Okay. So the total flow, so this surface is made up of n such infinitesimal surfaces. So you have to integrate over ds to find the total flow through the entire surface. So you have to do this integration v dot n cap ds. All right. Again, if you remember the physical significance of divergence, it is the flux, right? So we know that the outflow through a volume d tau is called the flux, and it is given by divergence v d tau. We had discussed this when we were discussing the physical significance of the divergence of a vector. So if you have an infinitesimal volume d tau and the velocity vector is v, then divergence v gives you the flux per unit time per unit volume, and multiplying it by the volume d tau will give you the flow per unit time through a volume d tau. So this is what I'm talking about. Suppose you have a volume d tau equal to dx dy dz like this, then the outflow from this volume, all these arrows coming out, this is given by the divergence, and this is called the flux. Now let us consider, yes, any question? If anyone has any question, please stop, unmute yourself and ask me, because these are all very, very important concepts, and you need to be clear about what you are listening and what you are understanding. And this elaborate, picture and explanation is not given in any one particular book. I can hear somebody's microphone on, so if you have a question, then ask, otherwise please mute your microphone. Okay, so what I was telling is this kind of elaborate explanation with figure is not given in any one particular book. So, but your syllabus contains this specifically, physical interpretation of the divergence theorem. All right. So you need to listen to me properly and see if you are understanding. Okay. So we see that the flux is related to the quantity coming out from a given volume. Now what we do is, remember the surface that I had drawn in the earlier slide. Suppose we divide the volume that is enclosed by that closed surface into n compartments, each of volume d tau. Okay, so we had this surface which I claimed was a closed surface. So what I do is I divide this surface into small cells, all of equal volume, and each volume is d tau I. Okay, so these are the d tau i's. Pick up any such cell. Okay, the only imagination that you have to do over here is that here I have only been able to draw a two-dimensional picture. I don't yet know how to draw a three-dimensional picture. So you have to imagine that this is a three-dimensional object with the volumes d tau I. These are not just flat squares, these are actually cubes, cubical cells. Okay. So the outflow from each such compartment, according to our interpretation of flux, is divergence V d tau. All right. So for all n compartments, I said I'm dividing this entire enclosure into n compartments. So for all the n compartments, the total outflow will be given by summing this up. So summation I divergence V d tau I is the total outflow. However, if you consider the interior of this of this enclosure over here, then it is easy to imagine that the flow from adjacent compartments will cancel each other out because all of them are of the same volume. So flow from all of them, outflow from each of them is divergence V d tau I. So, the amount coming from this compartment to this will be equal to the amount coming from this to this. Similarly, for a compartment like this, similarly here, or even if you consider vertical flow, then flow between adjacent compartments are equal and they will cancel each other out in the core of the body of the enclosure, because all of them we have imagined to be, we have divided up into equal number. Now just remember one thing, these compartments are not actually present. We have imagined dividing the enclosure up into such compartments. Okay, so the net outflow will only be that through the surface. Only the compartments that are lying at the surface will have something that are flowing outside too. Apart from that is flowing inside. So basically this summation, actually what is remaining of this is that flowing out through the surface, outer surface. So in the limit when these compartments are of very small volume, that is d tau goes to 0, we can go from discrete to continuous, that is we can replace the summation by the volume integral, and therefore what we get is divergence V dV is equal to surface integral V dot n cap ds, because we saw in the last slide that the surface integral exactly gives us this, the flow through the surface, this quantity here. And from this volume interpretation, we see that the volume integral of divergence V dV is also giving us the flow through the outer surface. So this is why the divergence theorem can relate the surface integral over a closed surface to the volume integral of the volume enclosed for the same vector but the divergence of the vector. Okay, so I hope if you go through these two slides very minutely, and if you replay the recording if required, then you will be able to understand. At this point, does anyone have any question regarding this? Because after this I'll switch over to the problem of divergence theorem. Any question? can I at least ask you whether you have understood?
Ma'am, we've understood, and there's no question, ma'am.
Okay. So the divergence theorem basically therefore converts a volume integral into a closed surface integral and vice versa. And we'll see the utility of the divergence theorem very soon by doing a problem. Okay. So problem is, consider a vector. I've taken the simplest possible vector r equal to x I cap plus y j cap plus z k cap, and verify Gauss's divergence theorem for this vector over the closed surface of a cylinder given in the adjoining figure. So this is a cylinder. I set up the coordinate axis. This is the radius of the cylinder and this is the height of the cylinder. Okay, so we have to verify divergence theorem over this cylinder for the given vector, which is the simple position vector. Okay, solution. This is Gauss's divergence theorem. So we have to basically show that left hand side and right hand side are equal. Now first let us see what the left hand side gives us. Divergence of V is divergence of R, which is 3, all of you know that. So the left hand side is basically volume integral of divergence V dV. So volume integral of 3 dV, 3 is a constant, take it outside. Volume integral of dV. Now volume integral of dV will give you the volume of this cylinder, which is pi a square h. So the result of the left hand side is simply 3 pi a square h. You can see it's just almost a one step solution. Alright. Now let us look at the right hand side. Right hand side is surface integral, closed surface integral v dot n cap ds. So what we do is we divide the surface into 3 parts, S1, S2 and S3. So S1 is the top circle, S2 is the bottom circle and S3 is this curved surface of the cylinder. Clear? So one plane surface S1, another plane surface S2 and one curved surface S3. So remember, just keep notice of these small things. V dot n cap ds has a closed surface integral sign, but here since we have separated the surfaces, we do not write the closed surface integral sign anymore. So these are minute things which you must remember while doing these problems. Giving the vector sign, giving the cap, writing the circle for a closed surface, not writing the circle for an open surface, etc. So let us consider S1. For S1, n cap is k cap along the z axis. So r dot n cap is z, which is h. The value of z at this point is h. So r dot n cap s ds for the first surface. So this is h, it comes out. So integration s1 ds1. The value of this surface, the area, this will give you the area of this surface. This is the area of this circle of radius a, which is pi a square. So the first integration gives you pi a square h. Second surface is the bottom surface. N2 cap is minus k cap over here, outward normal. So r dot N2 cap is minus z, value is 0 according to the orientation of the cylinder that we have chosen. So value of the second surface integral is 0. Okay. Now we come to the third surface. Can you mute yourself, whoever has his microphone on? Now equation of the curved surface is x square plus y square equal to a square. Okay, this is the only step that is a bit, I shouldn't say difficult, but a little thought provoking. So the curved surface has an equation x square plus y square equal to a square. So basically to find the normal to this surface, you have to do the gradient. Okay. So N3 is grad phi by mod grad phi. Grad phi is 2xi cap plus 2yj cap divided by mod grad phi is this. Now 4 comes outside as 2. So you have x square plus y square. X square plus y square is a square. So root over a square is a. And 2 cancels with the 2 on the top. So you have the normal as xi cap plus yj cap divided by a. So r
Yes.
dot n3 cap. So r dot n3 cap is x squared plus y squared divided by a, but x squared plus y squared is a squared. So r dot n3 cap is just a. All right. So the integration over S3 r dot n3 ds3 is, this is a, so a comes outside. So integration, surface integration ds3. Now this will give you the total surface of the curved side of the cylinder, which according to the formula, as you know, is 2 pi ah. So this is 2 pi a square h. To take the sum of the three surface integrals s1, s2 and s3, you get 0 pi a square h, 2 pi a square h. So the total closed surface integral comes out to be 3 pi a square h, and that is equal to the value of the left hand side. Now this problem gives you two things actually. First of all, in fact not two, several things. First of all, you get to know what kind of problems you get from divergence theorem. Secondly, this is another exercise in surface integral, another exercise in volume integral too. Thirdly, it shows you how using Gauss's divergence theorem you can simplify your problem. So the surface integral, I shouldn't say difficult, but definitely cumbersome, because you have to take so many steps. In the example problems of surface integral that we did earlier too, we saw that they are not one step things. They are not difficult, but there are several steps, pretty long sums. Whereas by converting this into a volume integral, it becomes so easy. Okay. Similarly, you know, for if we had taken that cube, the first example of surface integral that we had done, you can see for yourself. You see, take the vector, find the divergence, and then see how you can perform the volume integral, and it will be a much easier sum than doing the 6 surface integrals separately. Okay, so anytime, depending on the symmetry of the problem, if you find that you are asked to find the surface integral, you can quickly convert it to a volume integral by using Gauss's divergence theorem, and the working out becomes easier. You just have to keep one very important thing in mind, is that the surface must be a closed surface and the volume must be the volume enclosed by this particular closed surface. Okay. Now the second theorem, I'll take 10 more minutes and I'll finish off the integration theorems today, so that you know both you and I are at peace with the amount of syllabus that is left to finish. So we have Stoke's theorem, the second one. So please ignore that, that's my son talking. So Stoke's theorem. What is Stoke's theorem? If S is an open two-sided surface bounded by a closed non-intersecting curve C, which is a simple closed curve, then for a given vector A having continuous derivatives, Stoke's theorem says closed line integral A dot dr is equal to surface integral curl A dot n cap ds. So whereas Gauss's divergence theorem converted a surface integral into a volume integral, Stoke's theorem is a relation between a line integral and the surface integral of the curl of the same vector. Okay? We have to remember that this, so just as I told you, relates an integral over an open surface. Just remember that this is an open surface, unlike Gauss's divergence theorem, but the boundary is a closed curve. Okay. So for example, if you take an arbitrary, so please follow the following examples very carefully to understand when you can apply Stoke's theorem. For example, I have drawn a very arbitrarily shaped closed curve, okay? Not at all symmetric, but this is enclosing a particular surface, right? This is two-dimensional. This is no longer three-dimensional, but this is enclosing the surface S, and C is the curve. And remember, we are traveling anti-clockwise. The positive direction means anti-clockwise direction. Okay, so Stoke's theorem is applicable here. S is the surface, C is the closed curve. However, an open surface like this, where this is a hemisphere and it is open, remember, this is like a bowl. This is the brim, this is open, okay? So not a closed the half globe type of thing. This is a bowl kind of a figure where S is the surface, the outer hemispherical surface, and C is the closed curve, which is the boundary of this surface. Okay, you can apply Stoke's theorem here too. So much so, you can apply Stoke's theorem, and this is the direction of the boundary. You can apply Stoke's theorem to such a surface too. Here I have given you the picture of a butterfly net, okay, where S is the surface, the net, which is an open surface, this is the rim. So this is the surface S, and C, this rim over here of the net, is the boundary in question, is a closed curve, and you can apply Stoke's theorem to such a surface too. So for applying Stoke's theorem, it is not necessary that the surface needs to be a two-dimensional surface. It can be a three-dimensional surface. It is not necessary that the surface has to be, you know, some symmetric regular figure. It can be any shape. Just two things need to be satisfied in order that Stoke's theorem may be applied. One is that the boundary must be a simple closed curve. Now, what do I mean by a simple closed curve? A simple closed curve means that the boundary does not intersect itself at any point, so that such closed curves are applicable. These are also closed curves, but these are not simple closed curves because they intersect themselves at several or one point. So these, if you have an open surface whose boundary looks like this, then that is not a case where you can apply Stoke's theorem. Or the surface must be open and two-sided with two defined normals at any given point. So if you look at the first surface, you know, at any point you can consider two normals, one outward, one inward. The second figure, at any point two normals, one outward, one inward. For the net 2, you can see two normals, one outward, one inward at any point. You take any other point on this surface or this surface or this surface, you can find two normals at any given point. Okay, but if you take the example, most surfaces, I would say 99% of open surfaces in this universe are two-sided, but there are exceptions. For example, the Mobius strip. If you take a Mobius strip, those who are interested, you can Google out a Mobius strip. A Mobius strip is something like this, and at any point you do not get two defined normals. Why am I saying this? For example, if you follow my arrow here, if I start from here, say this is the direction of the normal and I'm on the outer surface now. Now if I travel around the Mobius strip, I'm still on the outer surface, on the outer surface, on the outer surface, on the outer surface. But you see, without lifting my arrow, I have now moved to the inner surface. Okay, and I'm on the inner surface, and without lifting I can again come to the outer surface. So what I'm trying to say is that if you have a surface like this, like the Mobius strip, then you cannot define a normal to be outward or inward exclusive. For such surfaces, you cannot apply Stoke's theorem. Okay. So next, again we move on to a problem as usual for Stoke's theorem. You have to prove, usually divergence theorem and Stoke's theorem etc. are, even the third one, the Green's theorem, are usually proof kind of problems. So you are given a vector and you are asked to prove Stoke's theorem for a square. So this is a square on which you have to prove this. Okay. So for the left hand side, a dot dr is for this problem b dot dr. Now we have divided up the closed line integral into 4 segments, a, b, c and d. Okay. So this is the direction a, b, c and d. So for the first integral a, b dot dr is along this, from this point to this point. So you can see that it is okay, 4. Okay. So v dot dr is 4y dx plus x dy plus 2z dz. So for the first step, that is small a, dy is 0. There is no dz over here. We are confined to the xy plane. So it comes out to be 4y dx because only x changes. But along this line, y is 0. So it comes out to be 0. Along the second line, we have x dy. Why? Because x, the value of x does not change over here. So dx is 0. So we are just left with x dy. Okay. Now the value of x is constant at 1. So I put x equal to 1. So integration 0 to 1 dy, which gives you 1. Segment here to here. Again, y does not change. So we don't have to bother about dy. We just have 4y dx. Value of y is constant at 1. So 4 into 1 dx. Now we are going from 1 to 0. So this is minus 4. And finally, from here to here along d, again x does not change. So dx is 0. We are only left with x dy. But value of x along this line is 0. So this is 0. So these are the 4 values we get. So the closed line integral becomes 0 plus 1 plus minus 4 plus 0 equal to minus 3. Now what is RHS? RHS is surface integral curl v dot n cap dx. So first we have to take curl v. Curl v, if you take, it gives you minus 3 k cap. So the left and right hand side becomes minus 3 k cap. N cap for this surface is along the z direction because this is confined to the xy plane. So minus 3 k cap dot k cap ds. So minus 3 comes outside. K cap dot k cap is 1. So integration s ds. Now what will this give you? This will give you the surface of this area, is this square, the surface area of this square. And this is a unit square. So surface area is 1. So this is minus 3. So you can see this is the same as the left hand side, which shows you that Stoke's theorem has been proved. Okay. Okay. Now you tell me, I have already overshooted by almost 10 minutes. It's totally up to you. You tell me, do you want me to continue with Green's theorem or will it be a bit overdose for one day?
Ma'am, I guess we should revise this once.
Okay. Yes, yeah, I thought I'll finish off, but usually there has not been any year where I have done surface integral, volume integral, and all 3 integration theorems together because yes, it's a bit of overdose. So what I'll do is I'll stop today. You revise these two the